So we've defined some big parts of Fourier analysis. We've learned how to express any data series in terms of the Fourier basis. We've learned how to compute the intensity at any given frequency. It's simplest if we're using a complex basis, but you can use cosine sine basis also if you want. Now we're ready to compute something called the periodogram. It's also sometimes called the power spectrum. For each frequency that satisfies that periodic boundary condition for all of our Fourier frequencies, we'll compute the Fourier coefficient and the intensity, which is the absolute square of that. Then we want to rescale the intensities. One complication is that scientists do not necessarily agree on how to rescale the intensities. Statisticians generally rescale it by multiplying it by n, the number of data points. So if the intensity is n times the absolute square of the Fourier coefficient, then the expected value of the intensity is equal to the variance of the noise. That's for white noise, for zero mean white noise. Geophysicists tend to rescale by 1 divided by the variance of the noise. So the intensity is 1 over sigma squared times the absolute square of the Fourier coefficient, in which case the expected value of the intensity is 1 divided by the number of data points. Astronomers tend to rescale it by n divided by sigma squared. N divided by sigma squared. This is the normalization, the scale factor I usually use. In that case, the intensity is n divided by sigma squared times the absolute square of the Fourier coefficient, and for white noise, the expected value of the intensity is equal to 1. All these scalings are valid. All of them make a perfectly valid periodogram or power spectrum. The one you choose may depend on what your personal preference is. Here's some white noise. Just plain old random white noise. I computed its Fourier transform to get cosine and sine coefficients. I then computed the power spectrum, the intensity at each Fourier frequency, using the astronomical normalization, which is what I'm used to. And I got this. They look kind of random, and in fact they are, and none of them has a power level which is big enough to indicate there's really periodic behavior going on. Here's something that does have a periodic signal as part of it. The data are a periodic signal with period of 10, or a frequency of 0.1, plus some white noise. When I compute the periodogram, I get this. Now I have extremely strong response at frequency 0.1 and very little response at other frequencies, and that's one of those telltale signs that these data probably have a periodic component to their signal with a frequency 0.1, which means a period of 10. By the way, we only compute usually the power spectrum at those Fourier frequencies. But we could compute it at other frequencies too. Our Fourier frequencies are chosen so they satisfy the periodic boundary condition, and because of that they form a complete orthonormal set. So we can express any set of data as its Fourier series, but what if the signal defined by the physics is periodic, but at some frequency which doesn't happen to be one of our Fourier frequencies? Now notice that the Fourier frequencies are equally spaced. They're 1 over t apart. What if the signal frequency is midway between two of them? Well, here's some data with a frequency of 0.105. Now, for this particular data, the total time span t is 100, so the Fourier frequencies are 0.01 apart. But I have a signal which isn't frequency 0.1, it's not frequency 0.11, it's right between them at 0.105. And what I've done is generate some data which are a signal at that frequency plus random noise. Now when I compute the periodogram, I get a strong response at 2 of the Fourier frequencies, at 0.1 and at 0.11. That's one of the signs that we might just have some periodic behavior, but at a frequency which is in between those two frequencies at which we're getting a strong response. One of the ways to investigate things in that kind of a situation is to compute the power spectrum, the periodogram, at other frequencies besides just our Fourier frequencies? Well, I generally do so, not just at the Fourier frequencies, but at 4 times as many frequencies. That is to say, for frequencies nu equal to integer divided by time, integer plus 1/4 divided by time, integer plus 1/2 divided by total time span, and integer plus 3/4 divided by total time span. This process is called oversampling the periodogram. Now, you wouldn't want to do this if you were going to express the data as a Fourier series, because then you'd have too many frequencies. You'd end up having redundant ones. And that's not really allowed when choosing a basis for a data space. But if you're just doing a periodogram so you can see what kind of periodic behavior might exist, it's a perfectly valid thing to do and sometimes a very useful thing to do. For instance, if we take that data we were just looking at and oversample the periodogram, we get this. Notice that we've got strong response at frequencies 0.1 and 0.11, just like we did before, but at frequency 0.105, we're getting a much stronger response. Generally, the strongest response will be at the actual signal frequency if there is a periodic signal. So that introduces the idea of oversampling a periodogram. Unfortunately, a lot of programs to compute the Fourier transform either won't oversample or they make it a bit difficult to do so. That's one of the reasons I ended up writing my own Fourier transform program. But oversampling, when you're trying to understand signals in observed time series, can be an extremely